Okay, hey everyone. So for today's session, I don't think anyone showed up, so I'm just gonna start recording the video so you can see it if you are busy. But today I was going to talk about electronic configurations. This covers module number 4, part 3, and this talks about a little more about shells, subshells, and writing an electronic configuration, but in a much more detailed way than we did last time. Last time we covered the way you write like 2, 8, 18. This one is much more detailed and involves subshells, and so that requires rigorous practice. So I would highly recommend practicing over and over for electronic configurations and asking me questions about it. Awesome. So I'm going to start with the first slide. I was going to talk about shells having energies. And so in the last session before the exam review, we discussed how electrons are localized in shells around the nucleus and not just anywhere randomly. And so every shell which has numbers, shell number 1, 2, 3, 4, as we go on, have different energy levels. So shell number 1, where n equals 1, has the energy level of 1 electron volts. Electron volts is like a unit, like a very, very small unit of measurements, very, very small unit for measuring energy, my bad. And so it's like joules, but much smaller, like 10 to the power negative 19 magnitude. So it's very small, like 19 zeros after decimal space. Okay, so that's n equals 1 has that energy level. And then I want to ask you as a question, what do you guys think would be the energy level for n equals 2? I don't want a number, just think about, would it be greater than this or smaller than this? And so I'm not going to, you don't have to pause the video or anything, but I would tell you the answer. The answer is n equals 2 would have a greater energy level. So n equals 2 lies somewhere, and the exact number for that is 11.2 eV. I don't think you need to memorize these numbers. There's no need to memorize these numbers, as it's too much. But the idea, big takeaway from this should be that you understand how the energy levels increase as shell number increases. So the idea for this slide is, do not memorize the electron volts number, but understand how energy level goes increasing as you go higher in the shell number. So the electrons who are in the outermost shell possess the highest amount of energy. Okay, let's keep drawing. The shell number 2. So then, by this logic, if shell number 1 has 1 eV and shell number 2 has 11.2 EVs, where do you think shell number 3 would lie on the spectrum? And so the answer would be higher than shell number 2. It's not very high comparatively. It's somewhere over here at 13.1 EV, n equals 3. And so we have an increase in energy, but the amount increase is smaller than the amount increase from 1 to 2. Okay, so the trend is it increases, but the rate of increase keeps going down as you go higher. So with this logic, you'll say n equals 4 is higher than n equals 3, but the distance is even smaller. So n equals 4 lies so much closer that it is 13.8 EV. Okay, at n equals 4. And so you can keep going up in this ladder, and like the distance will keep getting smaller and smaller. One more thing I want to talk about is excited state and ground state. And so you would hear these two words come up so many times in chemistry, again because almost all of chemistry revolves around excited states. And so, you know what, pause the video here, take a second, think about, and like ask yourself, what does excited state and ground states mean? And then once you've like spoken to yourself, talk to yourself, come back to the video and we'll discuss over it. And so if you're back and you ask yourself, what does ground state mean and what does excited state mean, you should have got these two answers. Ground state means that there's no extra energy in the electron, and excited state means that you provided or the electron received extra energy, so that it now is excited. And so let's talk about, for example, hydrogen atom. Z for hydrogen is 1. So in a hydrogen atom, there's only one electron. Okay, that makes it very easy. only one electron, it lies in this shell in n equals 1. It just revolves around nucleus in the one shell. And so if you happen to shine light on it of the right wavelength, it will get excited. And where would it go then? So once the electron gets excited, it jumps into a higher shell. And so it's no longer over here. Oops. It's no longer here, but now it lives in n equals 2, right? But think about this. Do things like to be in a higher energy state or a lower energy state? And the answer to that question is, in chemistry and physics and biology, always, almost always, things like to be in a lower energy state than a higher energy state. So there's literally no reason for the electron to stay in n equals 2, but it wants to come back to n equals 1. So what will happen now is, as you stop shining light on it, as you stop giving it more energy, it will stop being in this shell, and it will jump back down to n equals 1, right? Oops, my bad. And so what happened here was, while you excite, I'm going to use green. While you excited the electron, it received energy, and that's what made it jump up, right? But when it came back to the ground state, it gave off energy, and that's what made it come back down. So all the energy from 11.2 electron volts to 1 electron volt, the difference was 10 electron volts. So the height over here is of 10.2 eV, right? So when you provide it with 10.2 EVs, it goes from n equals 1 to n equals 2. But when you stop providing it, there's no reason for it to be there. So it wants to come back to a lower energy state. But energy cannot be created or destroyed. So all the energy it had in n equals 2 gets released away. It gets away, gets released, and then it comes back down to n equals 1. And all the energy was given out equates to the difference in the energy levels, which is 10.2 electron volts. And that's what the spectrum line you see in a hydrogen spectrum. Okay. And this happens at all stages. If you provide more energy, sometimes it might even jump to a high energy state. Like in my example, I made it jump one shell. It might go from here all the way to n equals 4. Okay. If you provide enough energy, like it needs to reach 13.8 EV, and you are at 1 EV. So if you provide it with 12.8 EV, it'll jump to this shell and then come back down at this stage after you stop giving it energy and release all the 12.8 EV provided. Okay, so that's called electron transitions. That's all I had to talk about this one. The next topic I was going to talk about is energy of different wavelengths. So why don't you pause the video, go back to your notes, or try to recall the equation for energy equals something, and it involves the wavelength. And so if you thought about E equals hc over lambda, you're exactly right. That's the formula for energy. And so in this formula, E is what you're finding. H and C are both constants, the Planck constant and the speed of light. Those numbers don't change. So what's changing is this number. So different wavelengths will give different answers to the formula. So different wavelengths have different energies. So I can say energy is proportional to the 1 over wavelength. Or another way to say that is energy is inversely proportional to wavelength. So as my wavelength increases, this fraction would get smaller and smaller. So my energy in the wave would also would decrease and not increase. Okay. So then let me redraw the graph I had before in the previous slide, where this is 1 EV, and then it was 11.2 EV, and then 13.1 EV, and 13.8 EV. Okay, and so EV is a unit of energy. Okay, it's like joules but smaller, I said. And so let's say I'm in transitions. My electron was at this stage, and it transitioned to n equals 1, compared to my electron was at this stage and transitioned to n equals 1. And then compare that to my electron was at this stage and it transitioned to n equals 1, 2, 3. So in my first case scenario, it goes from 3 to 1. In my second case scenario, it goes from 2 to 1. And in my third case scenario, it goes from 4 to 3. So my question to you now is, Out of these three examples, which of them, question one, has highest energy released? Ooh, how do you spell release? RELEASE. Okay, found it. Okay, so go ahead and pause the video and think about this question. So out of these three cases, case one, case two, and case three, which of the electron transitions would release the most amount of energy? And so if you the best way to solve this is just see which arrow jumping, like going down, is the biggest arrow. This arrow is only this long. This arrow is only this long, while this arrow is just so short. So out of these three, we can say this difference between the energy in going from state 3 to state 1 is the longest. So my case scenario 1 has the highest energy releasing, that is n equals 3 to 1 transition. Okay, if there was a transition from n equals 6 to 1, that would be even longer. So then that would be the highest one. So that's how you find energy released. And so my question to you now is, this energy is released, but in what form? Is it heat? Is it vibrations? Is it, what kind is it? So go ahead and pause the video. This is somewhere in the notes and the lecture slides. Think about it. When electrons transition from a higher state to a lower state, what form of energy is released? Okay, I mentioned that before in the last slide, and this has something to do with the hydrogen spectrum as well. So think about, in what form do electron transitions release energy? Because if you're back, the answer for the question is the energy released. In this case, let's use this sparkly one. The energy released in this case, all the energy released would be in the form of light. Okay, so when electrons jump from the higher energy to the lower energy, they release photons, because light is in the form of photons. Okay, and so photons can be treated as particles or waves, and so photons also have a lambda associated with them. So then my question is, question number 2 is, which transition has the greatest lambda? So out of these three case scenarios, which would have the highest wavelength? Okay, so pause the video, think about it, use this formula and this relationship, and then compare these three case scenarios and tell me which of them would have the highest lambda, which photon would have the highest lambda. And so if you're back, the way to solve this is, think about, higher the lambda, the lower the energy. So out of these three guys, the lowest energy transition would give you the highest lambda. And so this one is the smallest. So case scenario 3, I can't see the screen there. Okay, case scenario 3 gives you the smallest energy transition, hence the highest lambda. Okay, one quick note, like, I always get confused between things like, if something has a higher lambda, wouldn't it have higher energy? And that's just the way we think. Lambda is just the distance between two crests, right? Let me draw the different color. So that's a wave of like a long wavelength. And if we draw a wave of shorter wavelength, this wave has an even smaller lambda, correct? And so I keep saying that waves of longer wavelength have smaller energies, and waves of shorter wavelengths have higher energy. The reason for that is, the shorter the wavelength, the more amount of wave you can fit in a given time. So you're getting hit with more amount of wave in like 1 second. That's why waves of smaller wavelengths are not fast at the same speed, but they hit you with more amount of wave in the given segment of time than waves of higher wavelength. Okay, that's why they have higher energy. Another way to think about this is, if a basketball player, okay, take two basketball players, they're both dribbling the ball and walking with the same speed. Okay, so the velocity of the player is the same, but one of them dribbles the ball super fast, while the other dribbles the ball very slow. And so when they walk, If you trace the path of the ball, because they're dribbling, it will go up and down. The one who is dribbling faster would have a shorter wavelength. The ups and down would come very close to each other, while the player who is dribbling the ball very slowly will have a very relaxed wave path of the ball. And so if you get hit with one of those balls, the balls which was bouncing faster would have a higher energy, right? So the ball which bounces faster, or the wave which has a smaller wavelength, has a higher energy. And so that's the way I remember things. Because I find it really like counterintuitive to think about higher wavelengths should be higher energy, but that's wrong. That's incorrect. Shorter wavelengths is higher energy. Okay. Yep. So this is what I had for this slide. Uh, I realized I drew a lot on this slide, so go ahead and rewind the video if you want to like revisit things here and there. But okay, if you have questions about this, feel free to hit me up, ask me, ask your professor, ask your TA. They're super useful for this in this too. Okay, so moving on. Oh, I asked a question: which transition has the greatest energy? So the answer for this one would be you just find delta E. Okay, you just find the energy state of the highest energy subtracted by the lowest energy state, and then the difference, the bigger difference, the greater the energy. And the answer to this question would be use the relationship E is inversely proportional to lambda. So higher the E, smaller the lambda. Okay. Subshells. And so until now we've been talking about how electrons are localized in shells. And so scientists have figured out and realized that shells in like one shell can contain multiple subshells where electrons are localized. Okay. So review electron configuration. Okay. So I'm going to start with reviewing the older material where we talk about shells. And so we said shells have numbers like 1, 2, 3, 4, and like so on. And the capacity of a shell is given by the formula 2 times n squared, right? So when you put, if I want to find the capacity of n equals 1, I put n equals 1 over here. 1 squared is 1, and 1 times 2 is 2. So n can hold at the most 2 electrons. N equals 1 can hold at the most 2 electrons. If I want to find the capacity for n equals 2, I plug 2 in place of n. 2 squared is 4. 4 times 2 is 8. This one would be 3 squared is 9. 9 times 2 is 18. And this one would be 4 squared is 16. 16 times 2 is 32. And so these shells can hold as these many electrons. But scientists have figured out that these are also divided into subshells. And so there are 4 kinds of subshells you need to care about. They have names instead of numbers. The first one is called S, second one is called P, third one is called D, and fourth one is called F. Now do not worry about what these stand for. Just worry about remembering these 4 letters, S, P, D, and F. Okay. And so do you guys know which shells contain what subshells? If you know, I would recommend writing it down in the book before I give you the answer, so you can memorize it better. So if you're done writing it, the answer is shell number 1 only has S subshell. It does not have a subshell called P. Shell number 2 has subshells S and P. So these are repetitive. Okay. Okay, I'll come back to it. Shell number 3 has subshells S, P, and D. And shell number 4 has subshells S, P, D, and F. Okay. If there was a shell number 5, it would have S, P, D, F, and one more whose name I do not know. I don't think you didn't know either. But the idea is like the number of the shell number, whatever the number of the shell is, if it's shell number 2, shell number 3, that many subshells you'll have. As you see, like shell 1 is n equals 1, you only have 1 subshell. Your shell number 4 is n equals 4, you have 4 subshells. So n equals 5 would have 5 subshells. But don't worry about this. This is too high for you. You won't go that further in this class. So worry about until n equals 4. Okay. And so every shell contains the S subshell, and then starting from shell number 2, they all have the P subshell, and starting from shell number 3, they have the D subshell, and then shell number 4 has the F subshell. Okay. And so the way you would like address them is, if I want to talk about the S subshell in shell number 1, I would call it as 1s. Okay. If I want to talk about the D subshell in shell number 4, I would call it as the 4D subshell. Okay. This is very similar to writing your own like house address. You write a street number and then a building number. So think about shell numbers as street numbers and subshell numbers as building numbers. So now I would live on Union Drive 212 Bear Court. Okay, so I live in 4D subshell. And so electrons have addresses like that. And so every electron can be like appointed to one subshell and it will have its own address. Okay, cool. And so I want to take an example real quickly. Can we write the electronic configuration for chlorine? Okay, chlorine has Z equals 17. And so can you write down the electronic configuration? Don't worry about the subshells, only using the shells like 2, 8, whatever. So go ahead and pause the video at this point. Think about the electronic configuration for chlorine Z equals 17 in only terms of shells. Okay, so if you're back, the answer for this one would be it has 17 electrons, right? So I'm gonna count in my head. Shell 1 only has 2 electron capacity, so it's 2, comma. Now I have 15 left. Shell number 2 can only hold 8. So I'm out of the 15, I'm gonna put 8 in this shell. And so 15 minus 8 would be 7. And so shell number 3 can hold 18 electrons, but I only have 7 left. So I'm gonna put all of the 7s in the shell number 3. So my electron configuration with only shells for chlorine is 2, 8, 7. Okay. But if I want to include the SPDF subshells also in this one, there is a little detailed way of doing it, which I want to cover in the next slide, called as the Aufbau principle. Aufbau means building up. So this is how you fill up a shell. It is super hard to understand the very first time you see it, but I'll teach you how to do it. So when you start filling out shells, when you start filling out subshells, you follow these arrows, okay? So your first electron would enter this subshell, and then you move on, and then you go the next one, and then the next electrons enter this one, and then you move on, okay? And then you go back, and now you start from here, and the next electrons, whatever it is, goes into this subshell. If you have more electrons left, you keep moving to the next one, which is 3s, and you fill that one out. And then if you still have more left, you go down and then back up, okay? And one thing I forgot to tell you is, let me go to the back slide again. We said that electrons have, shells have capacities, right? Subshells also have capacities. And so S can only hold 2 electrons at the most. P can only hold 6 electrons at the most. D can only hold 10 electrons. And F can only hold 14 electrons. Okay, so I would memorize this as well. There is no formula for this. So you just have to memorize that S is 2, P is 6, D is 10, and F is 14. Okay, I think if you try to observe a pattern over here, you need to do +4, +4. Oh yeah, we found a pattern. Great. So as you increase 2, 3, 4, 5. Oh yeah. So every subshell consecutively can contain 4 more electrons. So if you start with the S as S equals capacity equals 2, 4 more for P would be 6, 4 more for D would be 10, and 4 more for F would be 14. Okay, I didn't know, but I just figured this out right now. So we found a way to remember the capacity of subshells. And so if I want to say how many subshells can I have in, how many electrons can I have in these subshells? So 1s, because it's an S subshell, would hold at the most 2 electrons. And so when writing, I would write those 2 electrons as a denotation on the exponent of the S. Okay, I'm not squaring it or something. It's just like a denotation writing I have 2 electrons in the S subshell. Okay, moving on, if I have to fill electrons in the 2s subshell, again it's an S, so I only put 2 at the most. Moving on, I go to 2p. Now p can hold more electrons. It can hold 6 electrons, so I can write at the most 2p6. It can be an event where I don't have enough electrons to fill, like in smaller atoms. I can go ahead and write 2p4 if I only have 4 electrons left, or 2p3 if I have 3 electrons left. But if I have to fill it to the maximum level, I would put 2p6. And 3s, if you guess, it'll be 2 again. 3p can hold 6, 4s can hold 2, 3D, now we said D can hold 10 electrons. So at the most, I can have 3D 10. I can have anything from 3D 1, 3D 2, 3D 3, all the way to 3D 10, but not 3D 11. Okay, and I keep going like that, keep going like that. Oh, I see a 4 over here for the first time. So I'm sorry, I can see a 4F over here. F can hold at the most 14 electrons. So I can have anything from 4F1, 4F2, 4F3, all the way to 4F14. Okay, so we first said that chlorine's electron configuration by the shell logic is 2,8,7. I'm sorry, 2,8,5. What was it? Oh, 2,8,7. I'm sorry, 2,8,7 by the shell electron configuration. Let's try filling it out using the Oppo principle for subshells. So I would start, you know what, the best thing to do, this is I draw lines for every electron I have in the atom. So 17, I want to draw 17 lines. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so it's easy for me to keep track of how many electrons are filled out. And so I'm going to start from 1s. 1s can hold at the most 2 electrons. So I'm going to go ahead and write 1s 2 and then take off 2 electrons. Then the line is over here. I jump off to the next one. I have 2s. 2s can hold at the most 2 electrons as well. So I would write 2s 2, take away 2 electrons. I'm done with that. I'm going to move next. The arrow ends. The next arrow starts from 2p6. Now 2p can hold at the most 6 electrons. So I'll take away 1, 2, 3, 4, 5, 6 electrons, and I'll fill that up. Okay, I still have 7 more to go. So I'm going to keep following the arrows. 2p6 follows 3s2. 3s can hold at the most 2. I'm going to take away 2 from here, put 2 over here, and then I still have 5 left. So I'm going to keep going. Arrow ends. The next arrow starts with 3p6. So 3p, it can hold 6 electrons. Let's see. 1, 2, 3, 4. I have 5 left. So I'm going to put all those 5 in 3p6, in 3p, and call it 3p5. So this is my electron configuration for the chlorine atom, which is 17. Okay, and that's how you write the complete electron configuration for chlorine. One quick note, like thing to notice over here, this 1 stands for shell 1. So my shell 1, I don't have any more 1s, right? I have 2s and 3s. Shell 1 contains only 2 electrons. Okay, then I have this 2 here and this 2 here. Nowhere else have 2s. So these 2 combined together gives me shell 2, right? Shell 2 has 2 plus 6, 8 electrons. Wow. And then I have shell number 3 over here. These combines give me 2 plus 5, 7. 7. This is exactly what we counted before using only shell configurations. Okay. So this is the same thing as before, except you just assign all these 8 electrons to even more particular subshells and assign all these 7 electrons to even more particular subshells. Okay, awesome. And so hope you guys understood how to do this. Feel free to go back and rewind the video and then see me do all of them again. But the next one is, I'm gonna do magic with you guys. I'm gonna make you guys pick a number from 1 to 36. Okay, pick a number in your head. Pick a number 1 to 36. Remember the number, don't tell me the number. Then go ahead and find the correct correct element from the table of that number. Okay, so you guys pick one, I'm gonna pick one, so we'll do it together. I pick number 14. Okay, let's randomly pick it out. So 14 lies over here is silicon. Now if you guys can't see the table properly, go ahead and Google it, and then whatever number you pick the correct element from there. Actually, I'm gonna pick a different one so I can do a more detailed example. I'm gonna pick iron, 26. Okay, so that's my number. You guys pick one, pick an element. Pause the video at this point. Try writing down the electronic configuration for the element you picked. I made you pick until 36 because then I didn't want it to be too big for you to like write down all of them. So 36 is a pretty big number. If you pick 36, you know, all the best doing it. But I'm gonna do iron. And so pause the video, write down electronic configuration. and then I'm gonna write mine over here. So iron Fe is 26. So I'm gonna start by drawing 26 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6. Okay. You can also like solve it with me. It's like a solve along. And so I'm gonna start with the first line, 1s2, and then take away 2 electrons. My next one is 2s, can hold 2 electrons. So I'm gonna take 2 and put 2s2. Now move ahead, pick up. Next one is 2p. 2p can hold 6 electrons. So I'm gonna write 1, 2, 3, 4, 5, 6, and then put 6 electrons here. Maximum. I'm done with 10. I still have plenty left to go. I'm gonna keep going. Next is 3s. 3s. S can hold 2. So I'm gonna take away 2 and then put them over here. I still have plenty left. Keep going. 3p. 3p can hold 6. So I'm gonna take away 1, 2, 3, 4, 5, 6 electrons and put them here. Keep going because I have plenty left to go. 4s. 4s. S can hold 2. Take away 2. Put them over here. I still have 6 left. After 4s, I go 3d. Yeah, 3d. I know d can hold 2 plus 4 plus 4, that's 10 electrons. So I'm going to count 1, 2, 3, 4, 5, 6. I only have 6 left, but I can hold 10. That's fine. I'm going to put the 6 here, let them live happily over there. And then so my electron configuration would be Fe26 equals 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Okay, and you see like the sequence is pretty consistent, right? The 1 and then 2s and then 3s, but then there's a 4 in the middle and a 3. That's completely fine. That's the way the electronic shells have energies, like subshells have energies. And so don't worry about that. Just remember how to make this thing. Oh, I didn't talk about that. Let me do that quickly. So to draw this, what you do is you simply write 1, 2, 3, 4, 5, 6, and then you skip 1, and for 2 you write 2 again, 3 again, 4 again, 5 again, 6 again. Then you skip 2, you write 3 again, 4 again, 5 again, and 6 again. You skip 3, you write 4, 5, and 6. Okay, and the entire first row you just call S. Okay, the entire second row you just call P. The entire third row you just call D. And the entire fourth row you just call F. Okay, and then my favorite part, I'm gonna take a pencil for this one. You start drawing diagonal lines through them. So there you go, there you go. Now careful. Oops, I messed up already. There you go. And then 2p and then 3s goes together. 3p, 4s goes together. So drawing the line is very tedious. So I would say draw all this very neatly. These go together. These go together. And you get the gist of it. So that's how you draw the upper principle if you had to draw it like during the exam. But once you draw it, like draw it on the side, and then while trying to solve the electrical fish, keep going back and looking at it. And so I'm gonna maybe take one more element so you can see how to fill out more of them. Let's take krypton. Okay, I'm gonna do it. I'm gonna take the biggest one I feared the most. I'm gonna take krypton and try writing it down. Now with krypton 36, I have so many electrons. I'm not gonna draw lines for it. I'm gonna do a pro gamer move. I'm gonna count them as I fill them out. And so if you see, there's a real quick trend notice here. These first three give 10 electrons. The next three also give 10 electrons. 3D itself, if completely filled, gives you 10 electrons. And then I don't know what happens after that. But I count electrons using this like quick math keeping. So I have to build 36, right? I'm gonna straight away copy this down. 1s2, 2s2, 2p6. So I already have 10 done, right? I have 26 left. I'm gonna do 3s2, 3p6, 4s2. I have 10 more like out of the way, so I have 16 left. 3D 10. 10 more gone. I have 6 left. Let me see what comes after 3D. 3D is here. Following 3D comes 4p. P can hold 6 electrons. And that's very convenient because I only had 6 left. Perfect. Okay. And so that's how you fill out electron configurations. Now, this is very hard to write because if you go to bigger like elements, this thing would go really long and then take up the entire page, maybe the next line. So what people do is people use if you notice, like if I take cobalt next, okay, cobalt would be is 27, would be very similar to iron, except it would be 3d7. Or if I take like gadolinium or germanium, it would have a common first part, but the next part would be different. And the common first part, if you trace back in the table, would be very similar or identical to the previous noble gas. So if I take iron, for example, again, iron is over here. So if I go back, the previous noble gas is argon, 18. So I'm going to count 18 electrons, would be this. Okay, these are 18 electrons, and this is also the electron configuration if I had to write for argon. So I can simply write 26 Fe is the same as square brackets argon square brackets, what's left is 4s2 3d6. And so this is my condensed electron configuration with my noble gas core. And so you might have to write in the exam in this way. Okay, I would honestly, if I was you, I would just like write down the entire thing and then let's find which is the previous one, count the electrons and put it in. I just find that to be easier. Professors say that this is easy to write. I just could never figure out, just like personally speaking. So if you had to write, I would just write the entire thing. Takes a few extra minutes, but gives you the right answer. Okay, and so that's the noble gas. Then these are the electrons which are in the outermost like side, or not in the core electrons. So these are the valence electrons left. Okay, so that's how you find how many valence electrons you have left. Okay, so another quick way of doing it is Fe iron is 26. The previous number is 18. So to find the valence electrons, not the valency, the valence electrons of iron, I would do 26 minus 18, which gives me 6, 7, 8. Okay, awesome. So that was the last thing I had for you guys. I would really highly recommend you to go back and pick out, maybe if you want to pick out more than like 3 or 4 elements you want and write the configurations for each of them in this way and see if they're right. To check if they're right, you can ask me, email me a picture of like what you wrote down. I'll tell you if it's right or wrong. Or if you want, you can always hit me up and then I could let me pull out a real quick video call and then solve it with you again. Okay, but this is something very tedious, and it's always helpful to keep practicing these things to get the hang of it. But that's all I had for today. I made a Kahoot quiz for you guys, which is like not really a quiz. It's supposed to like be a good closing for the sessions. But if you want, I can link the quiz in the description of the video, so go check that out. And I will see you guys on Sunday. Maybe on Sunday, if people show up, we can practice more of this and other questions you might have. But until then, have a good night and take care of yourself. How do I stop the recording now?